In this video, we're going to work through an active example of a research design that we would use the analysis of variance statistical procedure to analyze the differences between groups. And I'm going to begin with a very general question here. And this question is asking if standing balance performance among athletes is different between unique groups of those athletes. And in this study, I'm going to create 5 groups of different athletes, and within each group, I'm going to have 7 participants that meet certain criteria in order to be classified in each of those groups. And so the 5 groups here include basketball players, football players. Group 3 are composed of gymnasts, hockey players in group 4, and dancers in group 5. And so the overall question here is asking if dynamic balance performance is statistically different amongst these 5 groups. So are gymnasts superior than basketball players, or hockey players, or football players? So what we see here is a wide range of different combinations that we can apply our question to, and we need a robust type of statistical procedure in order to simultaneously examine for these differences, and the ANOVA procedure is just that procedure designed for this particular type of analysis. But to conduct the analysis, we need a measure, a quantitative assessment of that standing balance performance. And so we have to define our dependent variable, or sometimes referred to as our outcome variable, and in this case it's the number of balance falls in 1 minute. And so here we see in this picture a illustration of the task asked of all of these different athletes to perform, called a star excursion balance test. And so here we see a person standing on 1 foot, and they're going to reach out and just lightly tap the end of one part of the star, then they reach back and touch another, reach the diagonal, and they do this continuously for 1 minute. And what we're evaluating here is how many times the athlete quote unquote falls. And I don't mean fall over, but if the foot touches the ground in between the touching of one end of one part to the other end of another part, because they might lose balance, that's counted as 1 fall. And so we'll use some numbers to examine that. Now, the first step with any type of statistical approach here, using the null hypothesis approach, is to just start with a null hypothesis. And in this case, because we have 5 groups, we're going to state our null hypothesis that there are no differences among those groups. In other words, the average of the first group, which are the basketball players, will be equal to the average for the second group, and the third group, and the fourth, and the fifth, and so on and so forth. If the results confirm that, then we would conclude that there was no statistically significant differences among those 5 groups. But we also have to consider the alternative to that. And with the type of research design that has more than 2 groups of data that we're comparing, here we have 5 groups of data that we're comparing, we have a number of alternative hypotheses. So an alternative hypothesis in this case is anything that is not this up here, that is not the null hypothesis. So if we look at the first alternative, and this is actually should be H1 for alternative, so this is a typo here, make sure to fix that. Here we have the first group is not equal to the second group, but the second group is equal to the third group, and the fourth group, and the fifth group. And so this alternative hypothesis is not the same as this one. So that is one possibility. Here we see, once again, a typo, so this should be H1, that the not equal sign is between 2 and 3. And we have a not equal sign between 3 and 4. We have another one between 4 and 5. Now we have 2 not equal signs, and here we have 1, 2, 3, 4 not equal signs. And so we can actually apply even more alternative hypotheses. Now, this gets very cumbersome, but is there another way to express this in a much more efficient manner? And there is. And we would state, so this is not a typo here, so this is what we should have seen here. H1 for the alternative, we would just state simply that our first statement is false, that not all the mu's are equal. And this very general statement captures all of the possible combinations of alternative hypotheses. So this is where we begin our approach. Now what's next is that we conduct the study, we collect the data from the athletes that fit the characteristics of each of those 5 groups. And so from a research design, is this a true experimental design? And the answer to that question is no, because in this study, we don't have random assignments. So in order for a participant to be in each group, they have to meet the criteria of what a basketball player is, past experience and competitive history of a gymnast, football, hockey, dancers, so on and so forth. So in this study, this is a study that would be classified as a descriptive type of study, where we are describing the basic characteristics from a statistical perspective between these groups. Now, once we've collected the data, the first step is to make a table of the raw data. And so the raw data are the data collected from each person that we would enter and will enter into a statistical analysis. And then once we've done that, we decide on a statistical approach to move forward. And in this case, because we have more than 2 groups of data that we want to compare, we have the 5 groups, then we would use a 1-factor ANOVA. This one has no repeated measures. So we don't have the athletes crossing over into different groups. Each athlete is measured once for that particular test, and those data are entered into the analysis. So this is just a simple comparison between different groups. Now, what we see on slide number 9 here is a table of the hypothetical data obtained from the 7 participants in each of the 5 groups. And the first step we always do before we get into the more complex statistical procedures, in this case ANOVA, is we calculate descriptive statistics for each group. And that means we calculate the mean and the standard deviation for group 1, 2, 3, 4, and 5 separately. So when we look, we just take a quick scan, a visual scan of the averages. Here we see a range of responses here. If you just look at the raw data, it's very difficult to examine any particular pattern that might emerge. But when we calculate an average, that actually will highlight any unique pattern that exists. And so what we see here for group 2, we see an average number of falls of 7.86. For group 5, we see an average number of falls of only 4.43. And so what we want to ask here is, are those 2 scores statistically significant in terms of the difference? So we see scores that are closer to each other, and so the ANOVA procedure will identify that difference that exceeds what we might expect from random chance. Now, so we calculate the means for each group, and with the ANOVA procedure, we also calculate something called a grand mean, the overall average of all 35 scores. So if you had calculated the average of all 35 scores, you would get 5.77. Alternatively, if you calculate the average of the 5 averages, you would get 5.77. So by itself, this number here is not particularly meaningful because there are distinctive differences between the groups, but it is critical when we want to conduct the ANOVA procedure. So the overall average is something that is necessary that we'll get into in later parts for this unit. So once again here, the overall question we ask here, are the groups statistically different from each other? That's guiding our analysis. And so the next question is asking, how do the average scores between the different groups, how do those average scores vary with respect to each other and the grand mean? So we will have to consider the grand mean when we start calculating our ANOVA statistics. And so how do we measure this degree of variability? We calculate an average of somewhat of an average of the deviation scores, but those scores have to be squared. So that goes back to our first part of our unit here on slide number 5, where we step through the calculation of deviation all the way down to a sample variance. And now in terms of the ANOVA steps that we will cover in the next set of videos, the first step is to calculate the sum of squares, and I refer you back to slide number 5 for the general equation on how to do that, but we'll step through that as well. And recall that is a procedure where we add up the squared deviation scores. The next step is to calculate degrees of freedom. We saw that at the bottom of slide number 5 in the denominator, which was an n minus 1. Now with ANOVA, we have 3 different degrees of freedom values that we would have to calculate, and we'll certainly get to that. The third step is to calculate the average deviation scores, but now instead of calling it a variance, we call it a mean square. So the mean square, that is the accepted term in the ANOVA procedure, is mathematically a variance calculation. So once again here, slide number 5, review those steps on how to get to a variance in a general way, and then we'll make it more specific here with ANOVA. Now with the mean square, there are 2 mean square values to calculate that we will need, and we'll get to that. The next step, we're almost to the end here with the overall approach. We calculate the key statistic here, the F statistic, or F ratio, sometimes it's referred to. And from this point, I'm going to call it the F calculated or F obtained. This is the F statistic obtained from the data. So we carry out a bunch of calculations on the data that we have on slide number 9, and then that will culminate in this F statistic that we will then use to compare to what we call the critical F value. The critical F value is taken from the F table, and the only thing we need to know for the critical F value is the number of groups and our sample size. We don't need the actual measurements from the participants. The actual measurements will give us the F obtained. The sample size and the number of groups will guide us to selecting that critical F value that we will use as the threshold to compare our F statistic to. So this ends part 2 of our lecture on ANOVA.